Hi everybody, I'm presenting the next lecture here, and this lecture is the Griffith Medal lecture, and the laureate is Meinhard Kuna, who is somewhere here, around here. There you go. Meinhard became professor in 1997 in applied mechanics and solid mechanics at Technische Universität, the Bergakademie in Freiberg. Yes, not Freiburg. And 1997 was the year when we met also in the forest of Freiberg and having a workshop. 25 years ago, so real long. And now you are active retirement. That's what we call emeritus in the other country. Yeah. Emeritus professor. And you wrote a very popular book that became very popular, Finite Elements in Fracture Mechanics, and even got a medal for that, right? In Texti medal and a Wöhler medal in Germany. That must be the top notch. Wöhler was born in Hanover, so that's the place to get. So, and also everybody know that you were the chief editor of Engineering Fracture Mechanics until just recently. So now it's your time. Go ahead.
Hello. Yeah. Yeah. Good morning, everybody. Yeah. Thank you very much for the introducing words, and I very feel honored to receive the Griffith Medal from the ASIS. It's very yeah, and I also thank the organizers Pietro Moreira and Louis Rice to invite me here for this plenary lecture. I have chosen a topic which I found very interesting and which has not been so dealt with in the literature up to now. As well as from fundamental point of view, also from practical aspects. This is the anisotropy of crack growth. So we studied this in a project together with a Rolls-Royce company in Germany. It is a nickel-based alloy and thermomechanical fatigue crack growth. I want to introduce my co-workers. Dr. Ludwig did the main work. Mr. Rabold developed our code ProCrack for automated 3D crack growth, and from our partners Rolls-Royce, Germany, Dr. Schurig and Dr. Schlumps cooperated in this project. It doesn't work. Is it on or off? Okay. Fine. So, I want to bring a motivation at first to introduce in this specific problem, and then shortly I recap our finite element code ProCrack, which is able to simulate 3D fatigue crack growth in an automatic manner. Then I came to the very topic, the anisotropy of the fracture behavior in this special alloy, and we have to combine it with the TMF crack growth law, which is established at Rolls-Royce. And there experiments have been done on CT specimens, and we could simulate them and to verify or to validate, identify the parameters of our model. And finally, we applied this model to a typical component of a rotative, of a jet turbine. And then I close with conclusions. So everybody knows this modern civil aviation is based on such jet engines. This is one example from Rolls-Royce. It consists of a set of a cascade of discs, and where the blades are attached of various size for the various purposes. So the fresh air comes in here through the fan. Then we have a low pressure chamber to compress the air, and then a high pressure chamber, and then it goes to the combustion. And the materials have to withstand high inertia, centrifugal forces, and high temperature. So the typical materials are these nickel-based alloys like Udimate, Vespaloy, and Inconel. So we will focus on this disc here in the high pressure chamber. The design rules say if any blade would break, it must be contained in this jet engine. Yes? So the casing must not penetrate the casing and fly into the fuselage to destroy the aircraft or damage the passengers. But these discs here, they are so heavy and have so much kinetic energy. If they break, they cannot be prevented to cross the casing. And this happened in 2016 at Chicago Airport with a Boeing machine. It was just going to take off, and then the engine failed, so-called uncontained failure. And the engine caught fire, and the whole right wing burned down. The passengers could be rescued, fortunately. And my colleagues from Rolls-Royce asked me to point out that it was engine from their competitors in America, Pratt & Whitney. Not to mix it up. So what was the reason? It was a failure of such a disc. It started fatigue from a small internal inclusion here growing up, and then there's a final fracture, and it broke in several pieces and had so much kinetic energy that parts of them flow away through the casing 1 kilometer away and landed in an UPS warehouse near the airport. So, and they destroyed the wing and not the fuselage, and so it starts to burn. So if you look on the loading for such, this is a segment of such a disc, yes. Due to centrifugal forces, here at the borehole, it has to withstand high tensile strength, and all is, of course, thermomechanical and mechanical cycling. So it needs high low cycle fatigue resistance. Contrary here at the top, where the blades are attached, is have very high temperature, and we need high creep resistance. So these materials have to have all very good properties, combination of high strength, damage tolerance, creep, and oxidation resistance for these rotating parts. And Rolls-Royce developed an enhancement of Inconel 718. It is called A718 Plus. It has better strength, higher thermal stability, good workability, and can also be welded. So this is the good side, but this material has an anisotropy. So if you make a fracture test in mode 1 with a CT specimen in a cyclic experiment, TMF experiment, yes, then the crack deflects from the symmetry line. And this was a shock for the design engineers, because all their rules to predict or design these components are no longer valid. You didn't know where the crack will go and when it will start. So it needs research. The reason is, I'll explain it in a minute, that we have some lines of delta phase precipitates, here with an angle alpha. Here you see the microstructure. The white lines are these precipitates. These are delta nickel neop precipitates. These are formed during the forging process of the material along the forging lines. And so if they made a fatigue test at circular corner crack specimens, so 120 seconds dwell time at 650 degrees, R ratio of 0.1, and these are the crack propagation laws. In different, they cut the specimens in different directions. The zero direction is more or less parallel to this precipitates, and here the material behaves very weak, a very fast crack propagation rate. These symbols, the red line. And contrary, in the two opposite directions, 90 degree here and 90 degree here, we find this crack growth rate, which were about 2 orders of magnitude lower. The supplier gave this green line, but it is worthless in view of the differences. So here, this schematic sketch shows maybe more insight. So this is a so-called weak direction parallel to the precipitations. Yeah, the RDN is great compared to the other direction. Here, where this direction and this direction, where the crack has to intersect these hard delta phases. And we define, these are about the same, so we can define one weak direction and 2 strong directions, perpendicular. So this is clear. Now we need a new criterion for the deflection. Where does the crack go? Yeah, in the real structure. And the next is how to incorporate it in the fatigue crack growth law. And finally, they wanted to have a numerical tool how to predict this behavior in a real component. So I start with the last, with the software simulations. This is, I only will shortly recap our code ProCrack for automatic 3D crack growth simulations. It has similar features in performance like, you know, Frank's 3D or ZenCrack or ZCrack or BZ. So we resort on linear elastic fracture mechanics, 3D with all modes mixed, and we perform an incremental analysis of crack extension by finite element meshes. Yeah? But we have some special functions. So first is we work only with Abacus as a computing horse, so to say, and around it we formulate a collection of Python scripts. We use a submodel technique to calculate the k-factors very accurately, and for the separation of the modes we use the interaction integral, which is implemented in Abacus. Now, you know, for fatigue growth, the exact computation of the delta k is very important, because it goes to the power of n. Until now, we have implemented the classical Paris-Erdogan and the Nasgrove equations, but now we have to extend it to this thermomechanical fatigue. So this is a short overview of the flow chart. What is in red is added by us, the functions, and black is what we use from Abacus. So we start with usual input data of the structure with the crack geometry, loading material parameters, and some control files, and then generate by Abacus CAA the global FEM model of this crack component. Then it is analyzed, and from this result we cut out a submodel of the near crack environment. This is again transferred to Abacus to calculate now accurately the fracture parameters, and then we make decisions. Here's this decision block. If we have arrest or critical crack growth, and then we compute the new crack from coordinates, check against failure, and then we adapt the shape of the crack and continue in this loop. Here you see an example. So this should be the global structure, the model which we can automatically measure with tetrahedral elements, and from here with a semi-elliptical surface crack. Then we cut out a submodel, which is a tube-like structure with fan-shaped hexahedral elements and special crack tip elements. That's a crack tip, and this is run again, and we get the k-factors. Since we have mixed mode, we have to define an equivalent k-factor range for mixed mode, and here we adopt this method from Richard. We we see our initial example, initial crack phase, 2 steps of crack growth. We describe the crack growth by geometrical issues, these facets, not by element mesh itself. Yeah, so it is later meshed. We have the freedom of meshing it. So, and this is the current crack one, and we have several points here. And at these points, we have to decide where the crack goes and how much it goes, yeah, from our fracture mechanics criteria. And the deflection out of plane is controlled in this code by the maximum stress criterion. So here you see how the curved crack form can evolve for this example. It is a classical benchmark problem for such cases, a 3-point bend specimen, which has a crack which is inclined to the bending axis by 60 degrees. It starts from this inclination, and if you see this simulation, this is a global mesh. The crack turns into the direction to the symmetry line, so perpendicular to the maximum principal stress. So it wants to find mode run solutions. These are the stresses. Okay, we have applied this code to many industrial partners for wind turbines, for automotive industry, for Siemens Energy, and so on. And last year, one student made a master thesis where he compared our code with Frank 3D, which is, so to say, the standard. And this is one example from this. Here's a so-called NASA Louis Spur gear. It is a gear, and the tooths are cyclically loaded. And here at this notch, the crack would start. And the question is, where does it go? It depends on the thickness of the rim compared to the 2 steps. And for this example, it goes in this way. This is our mesh, and this is already these other facets of the progressive crack growth. And here's a comparison with Frank 3D, the K factors versus the crack size. So we find a very good agreement, and consequently all the crack growth simulations, so crack size versus numbers of cycles, fit very well. And moreover, the crack trajectories are the same in both simulations. But this results in a fracture of the rim, which is most detrimental. If the tooth would break, it would better. So thanks to Mr. Dule. So now let's come to the problem. I recap the isotropic criterion, the maximum principal stress criterion. Everybody of you knows it. Yes? So in 2D, we have the circumferential stresses, sigma, theta, theta, and a radius r around the crack tip. They can be described by the K factors in this well-known formula. And the maximum principal stress criterion says, and that the crack goes in that direction where the sigma, theta, theta has its maximum. Yeah? For an isotropic material. Isotropic deformation behavior and isotropic crack behavior. Our material is isotropic in the elastic behavior, but not in the fracture behavior. So, and I looked into the literature, what has been investigated for anisotropic crack growth. It is not complete, but most works is done on composite materials. It's clear, composite materials have this anisotropy in crack propagation. The first were Bucek and Herakovic in 1985. Then Carloni and Nobile applies the strain energy density criterion. Redefines the MTS criterion, and Hute and others use the J integral vector. And this is all 2D linear elastic. And the only 3D work I found is a PhD thesis of Petit at Cornell University in 2000. None of this literature is dealing with thermomechanical fatigue and creep. So we had to find a new criterion. And our idea is the following. The crack goes in that direction where it is highest stress compared to its resistance. So we form a quotient between the applied stress. This is the same which I shown in the previous formula, the circumferential stress, and over this function which says the resistance of crack growth in every direction around theta. So, and when this ratio has a maximum, the crack will follow this direction. So yes, loading compared to resistance has a maximum. So in our case, it is 3D, it's a little bit more complicated. So here we have one point of the crack tip. Is better? Yeah. And we have a coordinate system here, x1, x2, which moves with the crack front parallel. And we look for that direction n into which the crack will deflect. So the critical angle theta c. And our precipitates, they have any orientation. Yes, so they are defined by this normal vector m at this point. Yeah. So, and we introduce for this resistance curve this formula. We introduce two material parameters, delta k for the strong and delta k for the weak direction. This is not a k factor, it is only as a resistance measure. And it turned out that not the absolute values are important, but only the ratio. So how stronger beta, how stronger is the strong side compared to the weak direction. And between them we make such an, say, interpolation by the scalar product between this unit normal vector and this unit normal vector and square it. Maybe it becomes more apparent. This is this formula. If we consider the simple cases here, let's start here, where the crack goes parallel to the precipitates. So m and n have the same direction. The scalar product is 1, and we arrive that the critical stress is exactly this value for the weak direction. Contrary, if we have the other two directions where n and m are orthogonal to each other, then the scalar product is 0. Or here it's orthogonal, but it is out of plane. It's also 0. So we arrive with a strong value. But important is in between all other directions, this function here interpolates. Now we have another complication, because this orientation of the anisotropy is not unique in the whole structure. There's no homogeneous anisotropy, it is heterogeneous. So due to the forging lines, you see the forging lines, there's a piece is forged, and then from there the wheel or the disc is machined. So we had to, by an additional data file, we had to describe the shape of these lines and always the normal vectors. Okay, now we have the direction, and now we look for the propagation rate. And this is a so-called tidy model developed here by Timberland and co-workers, which is well established in Rolls-Royce. And it consists of a classical fatigue park, the Paris law, here with the effective stress intensity factor range and the Walker exponent for accounting for the R ratio. We have two C and N, two parameters, which are fortunately not dependent on the orientation, but they are dependent on temperature during the cycles. And here this term describes the time-dependent part due to oxidation and creep. The kernel is an Arrhenius function with this activation energy and this coefficient, and so it's clearly temperature dependent by this function T, temperature of time, and also here this exponent of time. And these two coefficients, A and B, they are orientation dependent. Yeah? And temperature dependence is introduced here and here. And you see the loading is described by the absolute value of the K factor. So we consider here small scale creeping. Creeping is controlled by K factor, the small creep zone. Yeah? And for these parameters, we also need to interpolate along the different directions. Yeah, this second integral has to be integrated. I skip it. This is a numeric thing. Now let's come to the experiments. So Rolls-Royce conducted experiments where they cut CT specimens out from this forged piece in different orientations, alignments with different angles, alpha, with respect to the crack. And this was the TMF experiments, 650 degrees up and down, and R ratio of 0.1. Okay, and from the corner crack specimens, we have the parameters of A and B for the different two extreme directions. Length was measured with a potential drop method. So here you see the results for different inclination angles: 15 degree, 30 degree, 45 degree, 60 degree, 75 degree, and 90 degree. So the crack turns a little bit, but parallel to the alignment of the precipitates, and finally it follows it. So it's really strange effect. Yes. Under mode 1, also macroscopic mode 1 loading, locally. So we have then now simulated it. You see some stages of simulation with for alpha 45 degrees. And I put it wrong. And this is an example. You see for me the stress. It's nothing special. So now we need to identify the parameters. We have all parameters determined until now, but not this ratio between the strong and the weak direction. So we have to play with this coefficient. And what you see here is for the alpha 75 degrees. The experimental points are the dots, and the other lines are for the different beta values. So it depends, of course, on the beta. The higher the beta, the stronger is the deflection. Yeah. And now we did it for all angles and found that for the experimental dots and our simulations of the crack path agreed best with a fit of beta equal to 2. So we have determined all parameters for the crack deflection. Now the next point is how fast goes the crack. And so we also compared experiments here for alpha 15 and for alpha 75 degrees. The red dots are the experiments, so the n over the number of cycles. And the green lines are our simulations. For alpha 15, the crack very fast follows the new direction after about 20 cycles. For the hard declination, you see the crack needs many cycles to find the direction, but then it goes very fast. So now we have all in hand, and wanted to make an application example for such a disk. Here you see a sectorial segment. We cannot calculate the whole disk, but only the sectorial segment. Here the blades are mounted by the so-called fir trees. Yeah, we have only dummy blades here with equivalent weight. And what is detrimental if such a fir tree would break? Then the two blades flow away. Yeah. So we assume a crack, a corner crack here at the edge of this fir tree. Now we made again a submodel. Here two blades, and this is a disc, and here this fir tree. Here you see the deformations. Yeah. This is a submodel, and now we start our crack work. So first we need the loading. The loading was a typical flight cycle. Here you see the stresses versus time. It is about 2.5 hours flight, starting like take off, climbing, cruising, approaching, and landing, and thrust reverse. It is a stress, and this is the temperature in this structure. So here you see the results. These are the initial corner cracks. Left hand is for isotropic crack growth assumption, and the right one is for the new anisotropic. And here you see the evolution of cracks. And here you see it in this transparent view, you see it better. Each line here is a crack increment step in the numerics. Here we needed 19, and this corresponds to about 11 flight cycles. And here you see, with isotropic assumption, that the crack fairly follows a direction perpendicular to the maximum load, the centrifugal forces. Whereas for anisotropy, and the platelets are aligned in this direction, the crack will turn its direction more or less parallel. You see it here and here. And we could also only simulate 4,000 flights, and the crack attained already this size. Okay, these are the conclusions. So we developed a new fracture criterion for the crack growth direction in an anisotropic material. I think this is not only restricted to this nickel-based alloy. If you have another anisotropy material, composites, or what is now in additive manufacturing, we have also clear anisotropy in the direction parallel and perpendicular to the processing, or in rolled sheets. So we can use it. This criterion was implemented in our code ProCrack, and also the TMF crack growth law was especially adjusted, and we could verify or identify the parameters for this new criterion and crack growth law by means of specimen experiments, and finally apply it to the TMF from the special turbine component. So its outlook, what I've shown here now, is all resorting on linear elastic fracture mechanics, delta K and K. In the case if the plastic zone become larger, more deformation and creep, and more extended plastic zones, it would be no longer valid. So that's we develop at current an extended version of ProCrack. It's called ProCrack Plus. Mr. Garnish has reported here in this conference on Monday, and this is now capable to tackle these large inelastic deformations. So it means the plastic zones have to develop and carried on with the propagating crack, and is especially devoted to LCF and TMF applications. And we can't no longer stay with K factor, so we use the CTOD concept as a crack tip measure for crack growth processing. Here you see one of the first examples. It is exactly the same beam with the inclined crack, but now what you see here are the plastic zones which move with a crack. So we can tackle this, and here you see a cutout the plastic zones in the inner and the plastic zone at the surface. Here you nicely see the mode mixity which occurs here. So I thank you for your attention and acknowledge the funding from the German Federal Ministry of Economy.